Okay, so in this video, we're going to go through section 3.5, which is talking about residuals. So the first thing we want to do is kind of define residuals. So residuals help to determine if a linear or nonlinear curve is appropriate for the model of the data. So looking at the residual values will help us see if this actually is a linear relationship or if a curve would be a better model. So the formula for residuals is that I take the observed y value and subtract the predicted y value. So essentially it's y minus y hat. In context, this is the vertical distance from the actual plotted point to the point on the regression line. Sometimes they're calling this as the observed error, right? So I'm predicting something, but it's not necessarily going to be the same value that's on the data. So I have an example here that I just got from mathbits.com. So if I'm given the data set, so I have the points 1, 2, 2, 1, 3, 3.5, 4, 3, 5, 4.5. And this creates a linear regression equation, y hat equals 0.7x plus 0.7. They've plotted the scatter plot points using these purple diamonds. So those are our scatter plot points. And then they found the regression point. So remember, to do that, what they did is they plugged in the values for x into this equation. So each x value that was in our original data set, they plugged into the regression equation and got the output values. And so the red line segments are the residuals. So the residuals here are these red line segments. So they're telling you the difference or visually showing you the difference between the point and the predicted value. So we're just going to practice calculating those residuals. So again, we have the answer up there because I've given you the graph. But so if I'm calculating the residuals for x equals 2 and x equals 5, I have to start by calculating the predicted value for those. So for the predicted value, I'm plugging those numbers into this equation. So y hat is equal to 0.7 times 2 plus 0.7. And so if I calculate that value, I get 2.1. So I can see that that's correct here because that's the point that they gave. So then for my residual, remember that I'm taking y minus y hat. So the y value at 2 was 1. So I'm going to do 1 minus 2.1. And so that gives me a residual of negative 1.1. Remember that when it's negative, that means that this was an overestimate by 1.1. Okay, so that means that the predicted value overestimates the actual value by 1.1. Again, it's an overestimate because of the negative. So the negative tells me that it was an overestimate. If that's positive, it'll be an underestimate. I can see that visually too. So because the point was here, the predicted value is above it, right? It's over that value. So I'm going to do the same thing with 5. So this time I'm plugging 5 in instead of 2. So y hat is equal to 0.7 times 5 plus 0.7. So that means that if I calculate this, my predicted value is 4.2. If I look at, so that's good here, right? I got the right number. If I look at my original output, it's 4.5. If I think about that, that means it's 4.5. So to find my residual, I'm taking that y value, which was 4.5, and subtracting my predicted value, which is 4.2. So my residual is 4.5 minus 4.2. So that gives me 0.3 as my residual. So notice that it's positive, so that makes it an overestimate. sorry, not an overestimate. That makes it an underestimate by 0.3, right? So it's an underestimate because 4.2 is smaller than 4.5. That one was an overestimate because 2.1 was larger than 1. So then they talked about these residual graphs. So they calculated all of the residuals. So all those values, we have 2 of them, 1.1 and 0.3, and they plotted those with their x values. So for example, on this residual graph, the point 2, negative 1.1 represents the graph of that residual. The point 5, 0.3 represents the graph of that residual. So then something that is linear is going to still have a scattered graph for residuals. So if this graph didn't look all scattered, if it had something that had some kind of curved shape, then that would tell me that linear regression isn't a good model. So because if I were to connect these points, I get some weird zigzag, that tells me that linear model is a better fit than a curved one. So no specific pattern is an indicator that this was a good linear model. So the next example, we're going to talk about applying these equations. So based on data taken from airline fares and distances flown, it's determined that the equation of least squares regression line is y hat equals 102.5 plus 0.65x, where y hat is the predicted fare and x is the distance in miles. One of the flights was 500 miles and its residual was $115. What was the fare for this flight? So what we want to do is identify what we can with the equation. So if I know that the flight was 500 miles and x is distance in miles, that's telling me that x is 500. So what I can find with x right now is the predicted y value. So if I find the predicted y value, 102.5 plus 0.65 times 500, and I calculate that, that's going to give me a predicted fare as $427.50. Okay. So my predicted fare is $427.50. The other piece of information that they give us is the residual. So if the residual equals 115, remember that the residual is y minus y hat. So y minus y hat is 115. I know what y hat is. So I'm going to plug it into that equation. Notice that if I just add 427.5 to both sides of this equation, I will know what y is, what the actual fare for that flight was. So if I add 427.5, it tells me that the actual value for that fare was 542.5. Okay, so the fare was $542.50. Okay, so when they give me the residual equation with an x value, sorry, not the regression equation with an x value and the residual, I can use that essentially as a system to find the y value, which was the fare for the original flight. So I already talked about this last thing in This, where we talked about, this is scattered. And so that tells me that I have a linear model. So that's this example here. So a linear appropriate model would be something where there's a random pattern. So I could say that there is no pattern of the graph. So they're randomly spaced above and below the x-axis. If I have nonlinear model, they follow a pattern resembling a curve. And so notice that I have a U-shaped pattern and then an upside down or inverted U-shaped pattern in those non-examples. Those tell us that least squares regression line is not appropriate for the data set that we're given. So graphing the residuals is another way of being able to tell whether a linear model is good, as compared to the R value, right? So the R value in the previous section showed us that if it was close to 1, a linear model was good. And then visually looking at the residuals will tell us in this section.